Hi students, this is Alex here. In this video, we are going to verify Gauss divergence theorem for the given f vector over the cube bounded by x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equal to 1. Let's write the Gauss divergence theorem. It is double integral over the surface S f vector dot n cap ds, which is equal to triple integral over the volume V del dot f vector dv. Let's draw the cube bounded by these equations. For this, we are going to take three-dimensional axis, that is mutually perpendicular axis. Let's name this as x and this is y and this is z axis, and there is a unit vector I cap, j cap and k cap along these axes. Let's construct the cube. So we have a cube which is bounded by x equal to 0, x equal to 1. So everything is 1 unit. So let's mark 1 unit in the axis. So our cube will be something like this. So here, then it has to be same size. So I take same size as this and move it here. Then I have to complete the cube by joining these lines. So we got a cube. Let's name the vertices. This is O, A, B and C. Rest of the things we can name it in any way. Let's take this as let's take this as D, then this is E, then F, then G. Now we are going to take the left hand side of the Gauss divergence theorem, which is double integral over the surface S. So let's take LHS. It is double integral over the surface S f vector dot n cap ds. But here we have 6 surfaces. So I am going to split this into 6 parts. So the first part, I am going to take double integral over OADB, that is the bottom surface of the cube. So OADB, and this is f dot n cap ds. And at the same time, next I will take the top surface, which is GEFC with double integral and f dot n cap ds. Now coming to the front surface and the back surface, the front surface is double integral ADEG f vector dot n cap ds, and the back surface is double integral OBFC f dot n cap ds. And now we left with left side and the right side surfaces. Left side is OAGC. So let's take plus double integral OAGC f vector dot n cap ds, and the right surface is double integral over DBFE. DBFE. This is DBFE and f vector dot n cap ds. And here everything is 1 unit. So if I mark this coordinate, this is y axis this is x-axis, so this is 1 comma 0 comma 0, and this is 0 comma 1 comma 0, and here it is z coordinate, so the vertex C is 0 comma 0 comma 1. And in every surface I have to find what is n cap. So from the diagram already we have written I direction, j direction and k direction. If we are any surface and the unit vector perpendicular to it, along these axes will be positive and opposite to that will be negative. Now coming to the first surface, here double integral. So we have OA dB f vector dot. So let's write f vector now as it is dot n cap. If I consider this bottom surface, this is the bottom surface, and if I take a unit vector perpendicular to it, it will be something like this. So we can see it is going away from the surface in a bottom direction, which is opposite to this k cap. So this n cap value here is minus k cap. So let's take it here, that is minus k cap, and this ds is nothing but, if we see this surface, it is having x value and y value. So it is dx into dy. So in the same way we have to write for other things. So this is dx into dy, and limit of this x is from 0 to 1, y is also from 0 to 1. So let's write the limit 0 to 1 here and 0 to 1 here. Now coming to the top surface. So now we completed the bottom surface. Now top surface is here. So in the same way we have to take, and this n cap for this surface will be something like this, and we see it is along the k direction. So it is plus k cap. Let's write it here, that is GEFC double integral, and even this limit is from 0 to 1 f vector dot k cap, and once again it is along the x value and y value we have, we don't have z value. So I can show it in the diagram. This is our x value and this is our y value. So again this will be dx into dy. So let's take dx dy. Now coming to this front surface. This front surface is here. You can see the front surface, and this k cap will be something like this. Sorry, n cap will be something like this. It is along the I direction, and this is having the sides this y and z. So this is y and z. So let's write it here, plus double integral over 0 to 1, 0 to 1, and f vector dot I cap, and this is dy and dz, and the next one in the same way 0 to 1, 0 to 1, f vector dot, it will be minus I cap, and dz dy dz. So in the same way another two more surfaces. One is left side from 0 to 1, 0 to 1 is a double integral f vector. When it goes left side, it will be minus j, and this will be, let's see it in the diagram. So this left surface is here, and this n cap goes in negative j direction, and it is having the dimensions along the x and z. X and z. So let's write it here. So this will be dx and dz, and the last one again right side surface 0 to 1, 0 to 1 f vector dot j cap into dx dz. And in every part we have to write the equation. That is, when it is a bottom surface, the surface is z is equal to 0 and top surface z value is 1. And in front surface the value of x is 1 and the back surface the value of x is 0, which we can see it here. So this is a bottom surface and in this surface the z value is 0 and in this surface top surface z value is 1. In the same way, front surface is the one this, which is x value is 1 and the back surface is this, which is x is 0. And the left side we have this surface where the value of the equation is y is 0 and in the right side we have the value of y is 1. Let's write it here. So this is y equal to 0 and y equal to 1. These are the respective equation of those surfaces. Now let's calculate each part separately. Taking the first one, I will take it as I1. We have double integral over 0 to 1, 0 to 1, f dot minus k cap. So when we do dot product, when I do with f dot k, we left with only yz term and it is minus k. So we have minus yz. So here it will be minus yz and the remaining are dx into dy. Dx, dy, and here the equation of this surface z is equal to 0. When we substitute 0 for z, the total value becomes 0. Then coming to the second part, z is 1. The same thing with positive sign. I will take it as I2, which is double integral 0 to 1, 0 to 1, and this is yz into dx dy. Since this surface is having z as 1, if I replace z as 1 in this part, the remaining will be y alone. So this will be double integral 0 to 1, 0 to 1 and y dx dy. Let's integrate this first with respect to x alone. So y is treated as a constant. So y will stay as it is and the x will be there, and when we substitute the limit 0 to 1 here and the remaining dy and integral 0 to 1 will be remaining as it is. When I substitute the upper limit minus lower limit, this becomes 1 and we left with only y integral 0 to 1 and dy, and this is y square by 2 and we have limit 0 to 1. This is 1 by 2. So coming to the third part of the integral, that is x is equal to 1 surface. So here let's take I3 and this is having double integral limit 0 to 1, 0 to 1, f dot we have I cap and the surface is x is equal to 1. So dot I, if we do with this f, we left with 4xz alone. So 4xz, 4xz, and this third integral surface is dy dz and x is equal to 1 is the surface. So dy dz and this surface is x is equal to 1. When I put 1 here, this will become double integral 0 to 1, 0 to 1, 4z dy dz, and first we are going to integrate this with respect to y. So z is a constant. So 4z will stay as it is and this is y, and y limit is from 0 to 1 and the remaining we have integral 0 to 1 and dz. When we replace the limit, this is 1 minus 0 which is 1. So totally 4z is remaining with the limit 0 to 1 and dz. When we integrate, it is 4z square by 2 and we have to substitute the limit 0 to 1. So this value is 4 into 1 by 2, which is 2. Coming to the I4, and here the value of x is 0. So what happens is we have I4 which is double integral 0 to 1 0 to 1 4xz dy dz, and when x is 0 the entire value becomes 0. Now coming to I phi. I phi is having f dot minus j, that is left side surface. So double integral 0 to 1 0 to 1 f dot minus j. So when I do dot product j with this f vector, we left with minus y square alone. So it is minus y square, and there is also a minus sign here. So minus j. So totally it will become plus. So plus y square, and this surface is having the equation which is written here, y is 0. So here it is y is 0 is the surface, and apart from that we have dx dz. Dx dz. Since y is 0, everything is 0. In the last part I6, which is double integral 0 to 1 0 to 1, it is actually, in the previous case it will become plus, and now this will become minus y square into dx and dz. So here it is dx and dz. Last is y is 1. So here the value of the equation, that is the surface equation, is y is equal to 1. So this becomes, so when we substitute y as 1, so this becomes minus 1, because y square in this place we substitute 1, but minus is outside, and we left with dx dz. First integration is with respect to x, so it means it will become minus x, and we have to substitute the limit 0 to 1. We left with dz integral 0 to 1. So this becomes, after substituting the limit, we get minus 1 minus 0, which is minus 1, integral 0 to 1 dz, and after integration we get minus z. Limit is from 0 to 1. This becomes minus 1. So totally the LHS part, by adding all the 6 integrals I1 to I6, I1 is 0, I2 is half. So 0 plus half, 0 plus half. Then I3 is 2, I4 is 0. So 2 plus 0, and I5 and I6 0 and minus 1. So plus 0 minus 1. So totally this is half, and combining these two this becomes 1. So finally half plus 1, after taking LCM, 1 plus 2, which is 3 by 2. Now we have to evaluate the right hand side of the Gauss divergence theorem, that is triple integral over the volume del dot f vector dv. Let's write it here separately. RHS, which is triple integral over the volume del dot f vector dv. So this is triple integral over the volume. Del is nothing but I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z, and with this dot of f vector, which is 4xz I cap minus y square j cap plus yz k cap. Then at the end we have dv. dv is dx dy dz, and in the cube we have all the limit of x, y, z is 0 to 1. So everything is 0 to 1, and I, if we do dot product, we get dou by dou x of 4xz, then minus dou by dou y of y square, and the last is dou by dou z of yz, and at the end we have dx, dy, dz. So partial derivative with respect to x, it means 4z constant which will stay as it is minus 2y, and the last term partial derivative with respect to z, that will be plus y, and we have triple integral. Everything is having the limit 0 to 1. This is dx, dy and dz, and we can combine these two terms. So triple integral 0 to 1, 0 to 1, 0 to 1, 4z minus y with respect to x, then y, then z. First, let's do the integration with respect to x. It means y and z are constants, so everything is a constant here, and integral of dx is x alone, and the limit is from 0 to 1. Rest of the two integral stays as it is, and at the end we have dy, dz. When we use the limit, it becomes 1, so it is 4z minus y. Now we have to do integral with respect to y, that is this part alone. And now other than y is constant, so 4z integration is 4z into y. Y integration is y square by 2. We have to use the limit from 0 to 1 for y, and outside we have integral with respect to z. When I substitute the limit 1, this becomes 4z minus 1 by 2, and now the lower limit will be 0. The last part which we have to integrate is with respect to z. So this is 4z square by 2 minus half z, and finally the limit is from 0 to 1. When we put the upper limit, it is 4 by 2, which is 2, minus 1 by 2, and the lower limit, everything is 0. So after taking LCM, this is 4 minus 1, which is 3 by 2. So we find LHS equal to RHS, hence Gauss divergence theorem is verified.